All right, guys, this is a good way for us to get some work done at home while we are not wasting valuable class time. So Edpuzzle, you watch it, you answer questions, you take your notes. It's a great way for you guys to spend your time. We're going to see how this works out for you the first time. I'm not sure if you're able to fast forward on Edpuzzle because I know on YouTube you can fast forward, play it at 2 times speed and things like that. So we're going to see how this first one goes. I'll get some feedback from you all. Let's go ahead and start talking about the nature of science. This is what science is all about, how where it came from, how it works, what we use it for. Natural philosophy is what the Western civilization, especially the ancient Greeks, came up with. Natural philosophy dealt with how the world works, and science actually came out of this. All science was called natural philosophy back in the day. So ancient Greeks, Socrates, Plato, Aristotle, the guys in the togas, they were the quote unquote authorities in Western thought all the way from 500 BC to about the time of Galileo in 1600 AD. And so they believed there was this ideal, a perfect world, but our world wasn't it. There must be some kind of true thing. So like you look at your table and the ancient Greeks would have thought like, well, maybe there's a true like ideal table, for example. So Aristotle's perfect world was accessible only though through thought experiments. Thought and contemplation was how they came up with this idea of an ideal or a perfect world. And observations and experiment in our sort of imperfect, mucky, dirty, nasty world was sort of useless in understanding their quote unquote timeless truth. So since the world was imperfect, they didn't look to observations or experiment the way we do today. And science, as we know it, did evolve from natural philosophy, literally thinking about nature. Francis Bacon, Galileo, many others around that time developed what we probably learned in grade school as a scientific method, right? And we'll talk a little bit about that. So in the last 400 years, scientists have made incredible strides in their efforts, but there is still much to know. For example, Galileo invented a telescope. He could see the planets, he could see their rotation. What he could see on Jupiter was much more, say, low res than what we could see now. You guys know about like the red spot on Jupiter and how it's like a swirling, spinning storm. He would have been able to see that from his telescope, but definitely not as sharp as the way we can see it now. So scientific progress brought about many technological progresses that Galileo could not have imagined. And science and technology are related, but they're not the same thing. And we'll talk more about that in a later presentation. Scientific methods, I use plural form of that because the progress of science has not been due to adherence of a simple-minded step-by-step process. You might have learned, and I even have a sign in my room about how it's, observation, experiment, data, results, conclusions, but it's much more circular than that. As long as your scientific method is evidence-based and it's repeatable and explains relationships, you're on the right track. You might come to a conclusion in one experiment and want to go back and test another. So our text says that the success of science has more to do with the attitude common to science than with a particular method. The attitude is one of inquiry, asking questions, experimentation, and humility before the facts. So if our data doesn't match up what we thought it was, we're going to be humble before the facts, and we're going to report on the data honestly. Let's keep this in mind. Science is a huge, complex enterprise. There's no pope of the science community, okay? There's no central governing body. So just about any generalization about scientific methods is not going to be strictly true. There's many ways to do the scientific method with the order as long as they follow the same criteria. So many people expect that certainty and absolute truth from science, and that's couldn't be further from the case. I think science opens up more mysteries than we care to know. The more you learn about the universe, the more questions come about. So as we talk about and use science in our class, we're going to use the same terminology, the same vocabulary. And keep in mind that the scientific meaning is often different than everyday meaning. Observation in science is something you notice. You can use your five senses for observation. It could be casual, it could be accidental. You've been doing this since you were born. You're observing that when you cried, your parents would come get you. Not all observations are correct. People do make mistakes. Some people might have observed that, when horses are running, all 4 feet are on the ground, or 2 are at the same time, or only 1 has to be on the ground when it's running. Not all observations are correct. People make mistakes. One of the questions that brought about film was people wanted to know if animals' legs are off the ground when they're running. Are all of them off the ground? Are 2 of them on the ground? And they were surprised to find out when they actually invented film, just to find out, if a horse runs, do his or her legs stay on the ground the whole time? So it's maybe what you notice wasn't correct, so people can make mistakes. All right. The primary way we have to tell if observation is correct is to repeat it, and have other competent people repeat it as well. So other scientists in the community, or the peers, like the peers in your class are your age group. When you go on trial, you get to be judged by a jury of your peers, other people like you in your same groupings, okay? So scientific observations must be repeatable. And these non-repeatable observations that they say are anecdotal evidence. I might say, anecdotally, I noticed a lot of people went to the bathroom last period. But a scientific observation would be like, I kept a data log of how many people signed out when they went to the bathroom. All right. So an observation that a lot of competent observers agree is correct is we generally call facts. All the scientific facts are not correct because people can make mistakes. So when we say fact, it's the best. It's the best that we know of now. Sometimes facts can be replaced. In the 1960s, they didn't know that there was a proton and a neutron in the nucleus of an atom. DNA was not known to have its double helix structure, right, until Watson and Crick. And so what happens is you have new technology, right? So like Rosalind Franklin analyzed the DNA, for example, with X-ray crystallography. That was the technology she used, and that helped Watson and Crick prove the double helix structure of DNA. All right, so technology and science are not the same, but they do help each other. And we'll talk more in another talk about science and tech and how it relates to you guys. Mr. Rossi, aren't facts true? Well, yeah, facts are true. We always think like it's a fact, like I jump up and down, gravity holds me down. That's a fact. But to the best of our current ability, that's all we can really say about facts, right? What's a conclusion? Conclusion is a decision based on observations, facts, or experimental data. I think what a conclusion too is an invitation to revise and reflect on your observations and your experiments. So we say that there's scientific laws. Don't break the laws of physics, okay? Or else the physics police will get you. It's a powerful summary of many facts is what it is. It means that it has been happening over and over again. Laws do describe what happened. They generally don't explain why they happen. So we do have like the law of gravity. Okay. Like I said earlier, it's a fact when I jump, I'm going to fall back down. Well, we know there's the law of gravity, but the theory of gravity isn't quite proven as to why it happens. Okay, there are a couple of different theories as to why it happens, but we're not definitively certain. We do know that it happens, and so these laws can be expressed repeatedly, conveniently, concisely in a mathematical form. We can calculate, how much of an effect gravity would have on you, for example. All right. So then what's a hypothesis? They always say in the elementary, middle school level, it's an educated guess. I want us to focus on it being a cause and effect relationship, why something happens. We're looking for cause and effect relationships. So it has to be testable, okay, with observation, and it has to be testable, with experimentation. So if it's not testable, you simply have a speculation. A hypothesis can be falsifiable. You can have a null hypothesis. Some scientists think that this is much more useful, and that some scientists will even insist that the hypothesis be falsifiable or null to ensure that everything is covered. We're going to focus on cause and effect in our hypotheses. All right. Let's look at theories. Theories versus laws are the language that I want to distinguish. So a theory is a synthesis, a very powerful combination of well-tested hypotheses. You probably learned about theory of evolution in biology class. It's very much accepted, right? And it's based on observations and evidence. And we're certain that it happened, but even though it's one of the most well-documented unifying theories of biology, it's still quote unquote just a theory. So we have to be careful with what we say. Our words in our everyday language versus our words in our science class have a couple of different meanings, right? These theories tend to explain why the laws operate the way they do. And the theories could also be called a model. Physical theories tend to be mathematical. And like I said, theory is like the most misused word in science. Let's just say that, you have facts that are revisable data about the world, and theories are interpreting those facts. Okay, so you have facts, they're observed over and over again, and the theory helps you explain why that phenomenon is happening. All right, science is a process. All right, in science, evidence for the truth of any idea is experimental observation. Not, tradition says we always did this, or someone's authority or anything else. So, the experts, 9 out of 10 dentists recommend this toothpaste. Well, unless we can prove that with evidence and experimentation, 9 out of 10 dentists doesn't really matter. Sorry, dentists. The process of science of testing facts, conclusions, laws, and theories, it never ends. It's an ongoing process. So we're always learning more and more about the universe, okay? I'm sure you guys have questions like, what is the universe made of? Did it begin with the Big Bang? Are black holes real? Can time travel be possible? All of these questions are never ending. And so, like, even if we find out an idea of a black hole, can we find evidence of a black hole, for example? And how would we do that? Do we have the technology? Are we developing the technology? Okay. In science, hardly anything is ever proven once and for all. It's very rare. It's okay to revise your understanding. It's okay to learn more. So science and tech are about discovering new things and applying those discoveries, right? If science is about discovering how the nature of things and how they work, technology is using these discoveries, and hopefully it's for good, right? Let's not use our science and technology for evil. All right. Science uses technology, technology uses science. They both use each other. Although science and technology are not the same, neither could exist for long without the other. Isn't that the truth? Let's categorize science as a way or a method of knowing, and technology as a way of doing. Okay. Oh, all right. I'm going to stop there. I'll talk more about technology in the next presentation and give you some examples of that. All right. But I'll leave you with this. Science is a way of knowing how like nuclear fission works. But technology is the nuclear power plant that puts that into action. And that's all for today.